Hi guys, now we are ready for chapter 11 where we are moving from the somewhat unrealistic scenario of comparing a sample to a population to now we are just going to be working with samples. So it's unrealistic to compare a sample to a population because most times we don't have access to the population, so we don't have any way to calculate their mean or standard deviation. So the summary of topics for this lecture, I'll start off with talking about the two different types of related samples designs that are appropriate for a t-test. Then I'll show you all the formulas for this t-test for related samples and deconstruct what those formulas tell you. And I will just warn you that the formulas for the t-test for related samples are very different than the formulas that you've seen in the past, because now we are going to be working with difference scores and not just adding up x values for a single sample. And you'll see that in a minute. Then I'll show you every single possible null and alternative hypothesis that you can have for the t-test for related samples. And these are also very different from what you've been used to seeing in the past, because remember, you used to make reference to the population mean within those hypotheses that you stated in step 1. Well, we don't have the population mean anymore, so it's going to be a little bit different than what you're used to, but it'll still be step 1 of the hypothesis test. And we'll still have step 2, finding the critical value, step 3, doing the calculations, and step 4, making the decision and stating the conclusion. Then I'm going to talk briefly about R squared as a measure of effect size for the t-test for related samples, and then I'm going to show you 3 separate examples of calculations and all 4 steps of the hypothesis test for the t-test for related samples. So before we get into the nitty-gritty about the different types of related samples designs, I first want to discuss some advantages about this type of design. So first and foremost, there's no need for those population parameters. So even if you do not know what the population mean and standard deviation is, it's okay. You can use a related samples design and just use samples to get all of the data that you need for your analysis. You can also study changes over time with the related samples design, specifically the repeated measures design, which we'll talk about here in a little bit. So this would be involved with like a longitudinal study where maybe you want to see how well the 3rd grade improves reading. So you could measure a group of students right before they begin the 3rd grade, then measure their reading ability again after they complete the 3rd grade. But as I'll talk about here in a little bit, there is some problems with the longitudinal design because maybe it's not 3rd grade that resulted in improvements in their reading ability. So you do the t-test and you see, oh, there's a significant improvement in reading ability. 3rd grade must be awesome. Well, maybe there was some physiological changes in their brain that resulted in their reading ability improving. Or maybe their parent became more involved in their life and was reading to them more at night, and that helped their reading. I don't know, any number of things that happened between the first measurement of their reading ability and the second measurement, other than the independent variable, which in this example would be 3rd grade, that would have an impact on reading ability, which is the dependent variable in that example. Another advantage of the related samples design, and probably the biggest advantage overall, is that this design controls for individual differences. So if you're in the repeated measures design, measuring the same group twice, or in the matched subjects design, where you're matching each pair based on pre-existing levels of the dependent variable, you are controlling for those individual differences that could result in differences in the measured dependent variable that aren't related to the independent variable that's being manipulated. So because of this, you do not need as large of a sample size because overall, the standard error is going to be much, much smaller when you're using a related samples design. So you don't have to have that huge sample size to shrink that standard error in hopes of getting a larger test statistic and significant findings for your data. So the first variation of the repeated measures design is when you only have one level of the independent variable. So this is when you have one group and they're measured before and then they're measured after some manipulation of the independent variable. So for our sake, let's go ahead and say that we are looking at the effect of some sort of drug on pain. So the participant, if you look at this top row here, it shows you a picture of the design. They get the drug, or they're measured for their pain. So let's say maybe they have to do some sort of physical activity until the pain is unbearable and they have to stop. And we measure how long until they stop because of pain. And that's our dependent variable, how long it takes for them to be in so much pain that they have to stop the activity. And the drug is our independent variable. So we measure how long they can do activity before it really hurts. Then we give them the drug, and then we measure it again and see if they have a lot longer time before they hurt after they take the drug. So that would be a repeated measures design, or in other words, a pre-test, post-test design. Now, there are some major problems with this. One is that differences in the post-test may be due to time. So if a great deal of time elapses between both measurements, it could be just the things that happened in between the two measurements that resulted in a difference in the post-test. So, going back to the third grader's example, maybe their brains developed more, so they're better readers after third grade than they were before third grade, regardless of third grade. Another problem is that the differences in the post-test could be due to the pre-test itself. So if we're thinking about the drug example, well, maybe the fact that they had some sort of physical activity the first time improved how much time they could spend doing physical activity before they were in pain the second time, because they were in slightly better shape or more used to the activity that they were being asked to do as part of the study. As related to the third grade example, maybe for some reason the pre-test, the reading ability test, prepared them better for the post-test, the reading ability test. So maybe just taking that test the first time, they'd already seen it before, so when they took it the second time, they did better on it because they knew what to expect. So there is a really fancy and very strong design called the Solomon Four Groups design. I'm not going to make you responsible for this design and for analyzing the type of data that you would have for this design. In this class, this requires a mixed factor ANOVA, which we aren't going to be doing. That's way beyond the scope of this class. But it's important for you to understand how you can overcome some of these major problems with the related or the repeated measures design. So in the Solomon Four Groups design, you have 4 different groups or 4 different samples with multiple people in each group, but different people in each group. So group A gets the pre-test, then gets some manipulation of the independent variable, and then gets the post-test. So we're measuring the dependent variable, we're manipulating something, we're measuring the dependent variable again to see if changes occurred. And like I mentioned before, that's really where we stop with this t-test that we're going to be talking about today. Then another group, they get measured, the dependent variable gets measured, the pre-test, then nothing happens, and then they get the dependent variable measured again in post-test. Then the third group of participants, they get no pre-test, so the dependent variable isn't measured initially. Then they get some manipulation of the independent variable, and then the dependent variable gets measured again. And then the fourth group, they don't receive a pre-test. They get no manipulation of the independent variable. Essentially, the only thing that they get is they have their dependent measure or dependent variable measured at time 2, and that's the only thing that they experience. So the reason that all 4 of these groups are important is because you can look to see if maybe differences in the post-test are due to time, or differences in the post-test are due to the pre-test and not due to the independent variable. So if the post-test for group B is significantly different from the post-test from group D, so if these two are significantly different, then chances are the pre-test is having an effect on the post-test. So these people got nothing, but they were measured at time 2. And these people were pre-tested, they didn't get any independent variable, and they were measured at time 2. So like I mentioned before, if we're talking about this experiment where participants who are in chronic pain are asked to come in and do physical activity as long as they can and stop when the pain becomes unbearable, well, maybe just doing that the first time is going to improve your time or extend the time that you can do it the second time because you're in better shape. You've done the activity before. You're stretched out. You're warmed up. So if you saw significant differences between these two post-tests, between the one that didn't get the pretest and the one that did get the pretest, both aren't getting the independent variable, then you'd be suspicious that differences in the post-test are actually due to the pretest. So another way that you can use the Solomon four groups design to assess whether or not these major problems with this design, or with the repeated measures design, are having an effect on your results, is you can compare the two pretests to the post-test for group D. So think about it. These pretests happened at time 1, and then this post-test happens at time 2, and we haven't manipulated the independent variable or given them drugs, and they didn't have a pretest that would have an influence on their post-test. So if these pretests for group A and B are significantly different for the post-test for group D, then we can be pretty suspicious that something that occurred between time 1 and time 2, other than the independent variable, is having an effect on these differences. So back to the pain example, maybe at time 1, the weather was really rainy and humid. And I know from living with my dad that when it's really rainy and humid outside, your pain tends to be stronger, especially if you have arthritis or back pain. Whereas maybe at time 2, the weather was really, really nice and sunny. So weather wasn't having an effect on how much pain they were in. So you may, just by accident, think that, oh, the drug worked. They were able to do this physical activity for longer without being in pain the second time. But maybe it's not due to the drug and it's due to the difference in weather, just for example. And finally, if the post-test for group A and C are significantly different, so group A gets the pretest, independent variable post-test, group C just gets the independent variable in the post-test, well then you might be suspicious that the pretest is having some sort of effect on how the independent variable works. So for instance, back to the drug and pain study, maybe doing a little bit of exercise as part of the experiment increases the efficacy of the drug that you're taking. It makes it more effective. So then that has like a double effect on the results at time 2. So you really think the drug's having a great effect, but it's not just the drug, it's the drug and exercise. Well, you could compare this post-test to this post-test when they just got the independent variable, the drug, without any of the pre-testing or the exercise to see if there's a difference there. Again, I'm not going to have you develop a Solomon four groups design, and the data for this type of design is far more sophisticated than what you'll be asked to analyze in this class, but I want to make you aware of it because it is the best strategy for overcoming these problems that are associated with the repeated measures design. Now, another variation of the repeated measures design is when you have two separate levels of the independent variable. So for instance, let's say we were wanting to look at the effect of morphine versus the effect of fentanyl on pain. So this is when one group's dependent variable is measured twice, but not just, okay, like this one, dependent variable is measured, then something's manipulated, they're given a drug, for instance, and then they're measured again. They're receiving two separate levels of the independent variable and are measured on the dependent variable immediately after getting that level of the independent variable or that treatment. So one of the major problems with this design is the order effects, meaning that maybe what happens at time 1 or the first level of the independent variable changes your dependent variable's reaction to the second level of the independent variable that happens at time 2. So, for example, maybe if you get morphine, let's say you come in to do the study, they give you morphine, they measure how long you can do physical activity before you're in extreme pain, and then the next day you come in and you get fentanyl. Well, maybe you've developed a tolerance, so fentanyl is not as effective. Or maybe the fentanyl is more effective because you still have some morphine in your system. So you can see how, the order could have an effect. So the best way to mitigate that problem is through counterbalancing. So that's when half of your participants get the first level of the independent variable and then the second level, and then the next half gets the second level and then the first level. So you're kind of weeding out those differences that could occur based on the first treatment that they received. Now, the second major type of related samples design is the matched or equivalent subjects design. So this is when you have two separate groups. Each person in each group is only measured on their dependent variable one time, and each person only receives one level of the independent variable. But the major difference here is that you have each group or each individual is matched to somebody else in the study based on their current level of the dependent variable or based on something very closely related to the dependent variable. So in other words, you want to find equivalent pairs so that you can technically treat each pair of subjects as the same person. Because for all intents and purposes, when it comes to what you're interested in studying, you've made them equivalent with regards to what you're measuring, the dependent variable. So for instance, if you were doing that pain study, level 1 could be morphine, level 2 could be fentanyl, and subject A and B would receive different drugs, but let's say that they were matched previously based on the amount of pain that they were in, or maybe the type of pain that they were experiencing. So maybe pair 1 both have chronic back pain to a similar degree, pair 2 both have arthritis, pair 3 both have multiple sclerosis, and so on and so forth. You're matching them based on the type of pain that they have and maybe even the level of pain, and then treating both people in this pair as the same person. So actually, trying to kind of mimic this design where one person is getting both drugs while overcoming the effects of the first treatment having an impact on how the second treatment affects the dependent variable. So you can see that this is quite a bit different because technically you have two different groups, but we're treating them as the people who are matched as the same person. Now, one of the major problems with this design is trying to find those equivalent pairs, and not only trying to find people who are equivalent, but also trying to determine the proper criteria for equivalence. So you have to really know pretty much everything that can have an impact on differences in the dependent variable, and then match them based on those criteria. So here are the formulas for the t-test for related samples, and no matter which kind of design, if it's the repeated measures with one independent variable or two independent levels of the independent variable, or if it is the matched subjects design, you're going to be using the same exact formulas. So let me break these down for you. This first one is for your t observed, or your final value in step 3. You'll notice that there are no population parameters here. You just have the sample mean and then the estimated standard error. But you'll also see that there are these D's here. So this stands for difference. So we're going to be looking at differences between time 1 and time 2 if we're doing the repeated measures design, or between each person and each pair. So you'll see D reflecting difference scores. But this still reflects the observed difference divided by the expected observed difference between groups or tests if the independent variable has no effect. This is still the standard error, well, the estimated standard error for the t-test. So here's the formula for standard error. It looks identical to what you saw for the t-test for the single sample. So you'll see that the standard deviation formula for the sample is the same as in the past, but don't be misled because the interpretation is different now. So the standard deviation for the sample used to give you a measure of the spread in scores in the sample. So how spread out are scores from the mean on average. Well, now this tells you the consistency of the treatment effect. So if you have a higher standard deviation, that means that there's a less predictable effect of the independent variable on the dependent variable. Or in other words, there's more spread. If you have a higher standard deviation, there's more spread in differences, not scores, but in differences. And it can be a spread in differences between time 1 and time 2, if you're doing the repeated measures design, or a spread in differences between each pair each person in the pair got a different level of the independent variable. But still, if you have a larger standard deviation, you'll have a larger standard error and you'll have a smaller t, all other things being held constant. Then the next formula, the sum of squares. This should look somewhat familiar, but x in the formula has been replaced with D. Remember, we're not worried about scores, we're worried about differences now between time 1 and time 2, or between each person and each pair. So sum of D squared, you'll have to square every single difference and add it together, minus the sum of D quantity squared, so you'll add up all the differences and square that, divided by n, which is the sample size. Then this is the mean difference, which is the sum of all the differences divided by how many different pairs or how many different people are in your sample. So one thing I want to point out, the n for both of these, and here, all these n's represent the number of participants if you're looking at the repeated measures design, or the number of matched pairs if you're looking at the matched subjects design. Or in other words, you can simply count how many rows you have. Each row represents one pair here, so we would have 7 would be our sample size. And each row represents one participant here. 1, 2, 3, 4, 5, 6 would be our sample size. So keep that in mind. And the reason that we don't count each one of these people as a unique person in this and say, oh, we have 14 people in this study, is because remember, we're treating, in this case, subject A and subject B as the same person because we matched them on something that's very relevant to the dependent variable ahead of time. So we're essentially treating them as the same person. And then finally, D difference just represents the difference between x2 minus x1. In the pretest, post-test, or the repeated measures design, those two terms are synonymous with each other. So you'd have the dependent variable for the post-test minus the measure of the dependent variable for the pretest for every single person in that study. Or if you were doing the matched subjects design, you would have the score for the second level of the independent variable, so the score on the dependent variable for the person in the pair who received the second level of the independent variable, minus the score for the dependent variable of the person who in the pair who got the first level of the independent variable. Now, all of this seems very abstract right now, but that's because we haven't done any examples to solidify your understanding. So if you're looking at all these symbols and you're kind of panicking, please don't panic. I'll show you 3 examples and we'll go through all of these steps. So now I want to talk about all the possible null and alternative hypotheses that you could have for the t-test of related samples. So the first scenario is you have a two-tailed test, so you're just expecting some sort of difference between the two levels of your independent variable or between your pre-test and your post-test. So for your alternative, you would have the mean difference is not equal to 0. Think about this. If there are some differences between time 2 and time 1, or between the treatment, the second treatment versus the first treatment, or the second level of the independent variable versus the first level of the independent variable, then this math will give you something other than 0. So if you think about if they're, rating their, or looking at how long it took before patients experience too much pain to keep doing physical activity, if, for example, in the matched pairs design, if the person who got fentanyl and the person who got morphine have the same exact time, then let's say it was 5 minutes, 5 minus 5 would give you 0. So that would be your null hypothesis, that there is no difference between the two different drugs. But your alternative would be supported more if, let's say, the person who got morphine only was able to do 5 minutes of activity before it was too painful, and then the person who got fentanyl had some different time, like 10 minutes or something like that. Then this math right here, the morphine minus the fentanyl, wouldn't give you 0. It would be something other than 0 because these wouldn't be the same. So I hope that helps you understand the rationale between the way that you state your null and your alternative hypothesis. So it could be a positive or a negative difference, just some difference in general, not equal to 0 when you figure out the difference. One-tailed, if you're expecting that your post-test would have higher scores, if you're doing a repeated measures design, or that the second treatment, the second level of your independent variable will result in higher scores on your dependent variable, then this is what your null and alternative would look like. So let's start with the alternative. So the mean difference, again, using population parameters, we're using mu here because we're using the sample to make inferences about the population. So the population is our reference point when we're stating our hypotheses. So the difference, the mean difference, would be greater than 0 if we think that post-test has higher scores, repeated measures design, or that treatment 2 has higher scores for the matched subjects design. So think about it. Let's stick with the post-test design, post-test, pre-test. Post-test higher than pre-test. Well, then when you do this math, you subtract a larger or a smaller number from a larger number, you end up with a positive difference. So we would expect that those differences altogether would result in a sum that's greater than 0, a positive difference. Time 2 larger than time 1 when you measure the dependent variable. Or treatment 2 results in a higher score for the dependent variable than treatment 1. Positive difference. Now, just like before, your null goes against your expectations, your alternative. So if it's not greater than 0, it's less than or equal to 0. So this would say, time 2 or the post-test actually had lower scores, so lower minus a higher number would result in a negative value, or treatment 1 actually had higher scores, or that there's no difference between time 1 and time 2 or treatment 1 and treatment 2. Stupid null going against what we think. Okay, third scenario, one-tailed test, where we're expecting that the post-test actually has lower scores, or treatment 2 results in lower scores on the dependent variable. So here, if you're thinking about post-test is lower minus the pre-test, which has a higher score on the dependent variable, you would end up with a negative number here. So you're expecting a negative difference. So your alternative would be the mean difference would be less than 0, negative, and your null would be the mean difference is greater than or equal to 0. So either a positive difference, meaning that the post-test actually had higher scores, or treatment 2 actually resulted in higher scores on the dependent variable, or that there's just no difference at all. So now let's take a look at effect size. So remember, I love R squared. It's my friend. I'm only going to talk about R squared for this t-test. And R squared has the same exact formula that it had for the t-test for single samples. You're going to be using the t that you calculate in step 3 based on the data, squaring it in the numerator and denominator, and then the denominator you're going to add the degrees of freedom, which in this case is still n minus 1. R squared still tells you the proportion of differences in the dependent variable, which can be accounted for by the independent variable. So, thinking about it as a pie and drawing out the pie and shading in the R squared times 100 to figure out what percentage of all the differences in whatever you're measuring can be accounted for by whatever you're manipulating. And then the criteria for R squared is still the same as it was for the t-test for the single sample. So let me walk you through the first of 3 example problems. So this is an example where we're looking at the impact of on-the-job training on job knowledge. So job knowledge is rated using a job knowledge exam score, and it's going from 1 to 8, 1 being very, very little job knowledge and 8 being a whole lot of job knowledge. So let's say that before we implement this on-the-job training company-wide, we want to make sure it works. So we randomly select 8 employees, and we measure their job knowledge both before and after receiving on-the-job training. So this would be similar to that first repeated measures design that I talked about, where there's a pre-test, job knowledge, manipulation of the independent variable, on-the-job training, and then a post-test. We're measuring job knowledge again afterwards. So what we are suspecting is that on-the-job training significantly improves scores on the job knowledge test. So in other words, we're expecting that their score after receiving on-the-job training, their score on job knowledge, will be higher than it was before receiving on-the-job training. So if you're thinking about the calculations for all these differences, we're going to expect that time 2 after on-the-job training will be consistently higher than time 1 before on-the-job training, and we're going to end up with a lot of positive differences here. So when we state our alternative hypothesis, we think that the mean difference will be greater than 0 or positive. The alternative, the mean difference would be less than or equal to 0. So maybe on-the-job training decreases job knowledge or has no effect. Then in step 2, to find your critical value, this is the same process that you used for the last t-test that you learned about. The only thing you need to be careful about is that make sure that you're not counting each of these scores here for your sample size. Just count the rows, because remember, this represents one person who was measured twice. So if you count these rows, you'll see that you have 8 employees. Don't think that I'm always going to tell you what the sample size is. You need to be able to find that on your own. And I also want to point out that you'll be just given data. I'm not going to give you these 2 columns here with the calculations that you need for T. Okay, back to T-crit. So our alpha level is 0.05. Our degrees of freedom, n minus 1, 8 minus 1 is 7. And we're looking at a one-tailed test just in the high end. We're thinking there's going to be an improvement between time 1 and time 2. So if you go to your table and you look this up, so degrees of freedom 7, one-tailed test, alpha 0.05. Let's make this a little bit bigger. Alpha level of 0.05, one tail. Remember, we're just looking at the high end. Degrees of freedom 7, and you land on 1.895. And you know it's positive 1.895 because we are only concerned with the high end of the distribution because we're expecting that time 2 will have larger scores. So now let's go through all these calculations. And just like I demonstrated in class, usually I write down the formula for the end result, the last formula I'm going to need, so T. And then I'm looking at this and I'm like, okay, I don't know what my mean difference is, so here's my formula that I wrote down for mean difference. I don't know what the estimated standard error of the difference is going to be, so I need to write down that formula. Then I look at the formulas that I wrote down and I say, okay, well, I don't know what the sum of D is, but I know how to get that by taking each X for the post-test and subtracting each X for the pre-test, or the measure of the dependent variables for each person, finding the differences. And then N, I already know N. So I'm done with that one. Then I look at this formula and I say, okay, well, I need to figure out my standard deviation. I already know N, so let's write down a formula for that. So here's that formula. Standard deviation equals the square root of the sum of squares over N minus 1. But I don't know what my sum of squares is, so I need to write down that formula, which is right here. And then in looking at this, I know I'm going to have my sum of D because I already calculated it to find my mean difference here. But I don't know what this sum of D squared is, or all the differences squared and added together is. So then you know you need to create this next column here to find all the squared D's. So I'll walk you through all these formulas. That was just the process for how to figure out all the formulas that you need. So the first step that I'm going to discuss is getting the mean difference. So the sum of all the differences divided by the total sample size. So to find the sum of those differences, you need to figure out all the D's for everybody in your sample and then add those together. And to find D, you take their score for the dependent variable or job knowledge at time 2 after on-the-job training and subtract it from their previous score before on-the-job training on job knowledge. So 5 minus 3, 5 minus 4, all the way down for everybody in the study. Then you find all those D values, add them together to get the sum of the differences. So the sum of the differences divided by the sample size, 12 divided by 8. 8 is our sample size. And you end up with a mean difference of 1.5. So on average, job knowledge changed by 1.5 points, increased by 1.5 points. Next thing I'm going to walk you through is finding the sum of squares for the differences. So you take each D value, each difference, and you square it, subtract by the sum of the differences squared, and then you divide that value by the sample size. So if you take each one of these D values and square it, 2 squared, 1 squared, 3 squared, 1 squared, 2 squared, 0 squared, 2 squared, and 1 squared, you get the squared version of those D values. Add those together, you get 24. Minus the sum of D, we already found that to be 12. That squared, divided by 8. Then you end up with 24 minus 12 squared is 144 divided by 8, which equals 24 minus 18. So 24 minus 144 divided by 8 is 18, and your sum of squares is 6. Then you plug that value into the formula for your standard deviation. So SS becomes 6. You just found it here. N minus 1, 8 minus 1. This becomes the square root of 6 divided by 7. 6 divided by 7 is 0.8571. Take the square root of that at the very end, and you get a standard deviation of 0.926. So on average, the difference between time 1 and time 2, or before and after on the job training, the average difference or standard difference in job knowledge scores is about 0.926 points away from the mean difference of 1.5. Now you want to find the standard error of the differences using the standard deviation that we just found, this 0.926. So replace S with 0.926 in the formula, dividing by the square root of the sample size. Then you end up with 0.926 divided by, well, the square root of 8 is 2.8284. Do that division and you end up with a standard error of 0.327. So what this says is that just randomly, just due to chance, we would expect to see about a 0.327 point difference between time 1 and time 2, even if on-the-job training had no effect on job knowledge. Now we plug in our standard error into our formula for the t-test for related samples and our mean difference. So replace the MD with the mean difference that we found, 1.5. Replace that SMD, or the standard error of the estimated standard error of the difference, with what we found, that 0.327. Do that division and you end up with 4.587 for your T observed, your T related samples, your calculation based on your data. Well, if you wanted to draw out your critical distribution, your critical region based on step 2, you would find that 4.587 falls in that tail. It exceeds the critical value of 1.895. So we could, going to step 4, reject the null hypothesis, and results suggest that on-the-job training did significantly increase job knowledge. So since we rejected the null hypothesis, and let's say we're trying to make an informed decision as to whether or not we should implement on-the-job training, we should probably look at the effect size, because it's not enough just to say, oh, well, we think it'll work in the population as well, but how much of an effect is it going to have on job knowledge? So you calculate R squared using T squared divided by T squared plus degrees of freedom, T squared, 4.587, divided by 4.587 squared plus 7 equals 21.0406 divided by 21.0406 plus 7, which is 28.0406, and you end up with 0.750, which is a large effect. Very large effect, really. Let's go ahead and just change this right now and say very large. All right. Next example. So that first example was a repeated measures design where we only manipulated one level of the independent variable, and we measured their dependent variable before and after. Well, now we're going to do an example where maybe we don't just want to look at on-the-job training by itself, but we want to see if on-the-job training coming from a peer versus coming from a supervisor has a different effect on job knowledge. So in this study, everybody in the study is getting both levels of the independent variable. They're getting peer based on the job training, and then they're getting supervisor based on the job training. Or if we're using counterbalancing, maybe this first 4 got peer first and then supervisor, and then the last 4 got supervisor first and then peer. but we are giving both levels of the independent variable to everybody in the study. So before I go through and I do show you all the calculations and we come up with our conclusion, think about what could be a possible problem or a flaw with this design. Remember, we're measuring job knowledge after they receive peer based on the job training, and then we're measuring job knowledge again after they receive supervisor based on the job training, or vice versa for half. So this design probably would not be appropriate because if you think about it, it's 100% chance that, let's say, for instance, the first half who get peer based on the job training first, they're going to be getting training. Their job knowledge is probably going to improve. And then when they get more training from their supervisor, they're going to have a new baseline for their knowledge to improve from because their knowledge already improved with the first round of training. And we're using the same job knowledge test twice. So not only are they going to learn more the second time they get training, regardless of who it's from, but they're taking the same test twice. They already know what's on it the second time they take it. So chances are they've probably paid more attention to the right things in the second round of training that they receive because they know what they're going to be tested on. And just through taking the test the first time, they're going to probably do better the second time. So think about that. And the next design that I show you would be the appropriate way to do this study. But just for our purposes, let's go through and assume that we are silly researchers who thought that this was a good idea. So this study is a two-tailed test because we're just saying that there's going to be some sort of difference. There's going to be a significantly different effect on scores for the job knowledge test depending on the job training from a supervisor versus on the job training from a peer. But we're not being specific. We don't know which one is going to be better. We just think that they're going to be different. So our alternative is that the difference will be not zero. There's some difference. And our null is that there won't be any difference whatsoever. But again, we're not being specific about do we think it's going to improve with supervisor or peer or be worse with supervisor or peer, just some sort of difference. Two-tailed test. We still have an alpha level of 0.05. Our degrees of freedom are still 7. We still have 1, 2, 3, 4, 5, 6, 7, 8 people in our study. But now we're using a two-tailed test. So let me show you how I got this critical value of 2.365. All right. Two-tailed test, alpha level of 0.05, degrees of freedom of 7, 2.365 is our critical value. All right. Keep in mind, it's positive or negative 2.365 because it's a two-tailed test, and as long as that mean difference falls outside of this range on either end of the distribution, we'll reject the null and say it's a significant finding. So I already walked you through the rationale for writing down the formulas, but I will walk you through all the numbers in all these formulas again. So the mean difference, looking at the sum of all the differences across all of the different people between supervisor on the job training and peer on the job training. And again, these numbers represent scores on the job knowledge test. Here, after they took peer on the job training. Here, scores on the job knowledge test after supervisor on the job training. So looking at all those differences between X2 and X1, or in this case, supervisor versus peer, 4 minus 6, 4 minus 5, 7 minus 4, all the way down, add those differences together, and you see that you get a negative 1. Now, it's important to note that it is good to have a negative and positive numbers here. Although we compensate for that when we go to our sum of squares, we get rid of those negatives because we just want a raw measure of the differences in general, not whether or not they're positive or negative differences. But here, this is really important. This is going to be the foundation for the numerator of our t-statistic, the mean difference. And if you think about it, yeah, okay, well, for this person, they learned more from peer based on the job training. This person, peer based on the job training. This person, supervisor based on the job training. This person, the same. This person learned more based on supervisor on the job training. More for supervisor on the job training. More for supervisor on the, or more for peer based on the job training, and more for peer based on the job training. It's not consistent. So this shrinks when you have some that were better at the second treatment and some that were better with the first treatment. So that kind of helps you really get a good sense of the fact that there are some differences, but the direction of those differences are not consistent when you figure out the sum of all those differences. So if you look at the mean difference, the sum of those differences, -1 divided by the sample size, 8, it's tiny. It's really small. So that means the numerator of your t-statistic is going to be really small. Then when you do the sum of squares, it's just an overall measure of the differences while getting rid of those negatives by squaring things. So the sum of d squared, you take each difference score, square it, add those together, you get 18, minus just the sum of d, -1, square that, divided by the sample size of 8. This becomes 18 minus 1 divided by 8, which becomes 18 minus 0.125, and you get a sum of squares of 17.875. Then you can plug that sum of squares in to your formula for the standard deviation, and now you have the square root of 17.875 divided by the sample size minus 1, or 8 minus 1, which becomes the square root of 17.875 divided by 7. 17.875 divided by 7 gives you 2.5536. Take the square root of that, and you end up with the standard deviation of 1.598. So on average, the spread of the differences is 1.598. And if you look at that, you can kind of see that resulting here. Like a lot of these are 1 or -1, the absolute value of 1. Then we've got, a 3 here and a couple of 2's that are dragging this number up a little bit higher than 1. The spread in these, the average spread in these differences is 1.598. Okay. Then we look at the mean difference, or the standard error for the mean difference here. So standard deviation, we just found 1.598 divided by the square root of the sample size, 8. Do all that math, and you end up with 0.565. So on average, just due to chance, we would expect that there would be about a 0.565 difference within the supervisor and peer based on the job training, just due to chance, even if peer based and supervisor based on the job training have no real difference in terms of their effect on job knowledge. Then plug your mean difference in the numerator, your standard error of the mean difference in your denominator, solve for t, and you end up with -0.221. That does not fall in either one of these tails, judging by your critical value. It's very small. So we would say we fail to reject the null hypothesis, and results suggest that peer based on the job training and supervisor based on the job training do not have a significantly different effect on scores on the job knowledge test. Last example. This is, remember with the previous example, I said that this is a flawed design because they're getting training, they're getting their job knowledge measured, and then they're getting training again, having their job knowledge measured again. So no matter who's giving them the training, they're going to probably be better the second time because they already received training previously and because they already took the same job knowledge test. So that's why a matched subjects design can be very desirable, even though it's hard to achieve because it is hard to match subjects into pairs. But in this case, it would be the best type of study to do. So now we want to look at the effect of peer based on the job training versus supervisor based on the job training on job knowledge. But instead of each person getting both types of training, we have two different people in each pair who are getting different types of training. So the first pair of people both had a job knowledge score of 2 before they got on the job training. And the next pair, they both had a score of 3 on the job knowledge test before training. So we're matching them literally on the dependent variable that was measured before they received training. You could also measure them on things like experience, cognitive ability, anything else that could have an impact on how well training impacts job knowledge. But to keep it simple, we just match them on their previous levels of job knowledge. So although this person who received peer based on the job training and this person who received supervisor based on the job training are different people, we're treating them as the same person because for our purposes, they are the same person. All we care about is their job knowledge. Okay, so same process, same math, same formulas as before. But in this case, for step 1, when we state our hypothesis, we're expecting that supervisor based on the job training significantly improves scores on the job knowledge test more than peer based. So now we're being specific. Let's say we did some research and we think that supervisor based on the job training is superior to peer based on the job training. So if you think about our x2 minus x1s, we're expecting that x2 is larger, supervisor based on the job training, the second level of our independent variable which is on the job training in this case. So we think that supervisor is better than peer. So in other words, we're expecting positive difference. Supervisor better than peer. So when we state our alternative, you want to say that the mean difference is positive, or in other words, the mean difference is greater than 0. And if it's not greater than 0, then it's less than or equal to 0 under the null. T-crit is the same T-crit that we found in this example, because again, we are doing a one-tailed test with the high end, still have a degrees of freedom of 7, we still have 8 people in our study, alpha level of 0.05. The calculations for step 3, starting with the mean difference, you just sum up all of the differences, all of the supervisor minus peer based on the job trainings. I didn't put the math here just because I needed room to show you, and I've showed you how you get these D's before. 5 minus 4 is 1, 5 minus 6 is negative 1, all the way down. And you end up with a sum of differences of negative 8. And as you can see, almost all of these differences are negative. So this isn't a good sign. This is kind of going against our alternative hypothesis, which states that supervisor based on the job training is actually better. Based on this, it appears that peer-based may be better. But to be a good researcher, you need to make your hypotheses before you have access to your data so that you do not capitalize on chance differences. So this may be surprising if you were actually following the process of true research where you state your hypothesis first and then get your data. So we've got our mean difference of negative 8 divided by sample size of 8. Again, we're not counting each person individually for the sample size. We're counting each pair because we're pretty much treating each person and each pair as the same person. And we do the math for the mean difference, we get negative 1. Not that impressive, but let's go ahead and see what happens. I mean, it's kind of big, but it's not in the right direction. Okay, sum of squares, sum of all the different scores squared minus the sum of the differences squared divided by the sample size. So you square each one of these differences, 1 times 1, negative 1 times negative 1. Remember, negative times a negative is a positive. That's why squaring gets rid of negatives. Negative 3 times negative 3 is 9, and so on and so forth, all the way down. Add those together, and you get 22. So you plug those in, you get 22 minus negative 8 squared divided by 8 becomes 22 minus 64 divided by 8. Negative 8 squared is 64. That becomes 22 minus 8, and you end up with the sum of squares of 14. Plug that 14 in for your sum of squares in your standard deviation formula. Do all that math, and you end up with 1.414. So the standard or average spread of the different scores is about 1.414, which makes sense if you look at the spread in these scores from negative 1. Remember, it's the spread in different scores from the mean differences. Then you plug in that 1.414 into your estimated standard error of the difference formula here. You've got your sample size, taking the square root of that into the denominator, do the math, you end up with 0.5. So, just due to random chance, even if there was no difference between peer based on the job training and supervisor based on the job training, we would expect there to be about a spread of 0.5 among all the different scores in the population. All right, t-test, our final calculation. Mean difference is negative 1 divided by the standard error of the mean difference. So how much of a mean difference would we think there would be just due to chance? And you end up with negative 2. So this is a pretty substantial difference. But guess what? It's negative. It doesn't match our original hypothesis that was a one-tailed hypothesis on the high end because, in fact, supervisor on the job training was less effective than pure based on the job training. So you can't really capitalize on chance and go back and go, actually, I meant that pure based was better and change it all up. As frustrating as it is as a scientist, you're supposed to do all of this in sequence. So this would fail to reject the null hypothesis. If this was a negative critical value, we would reject the null hypothesis, but it's not. We fail to reject, and results suggest that supervisor based on the job training does not significantly improve scores on the job knowledge test more than peer based on the job training. In fact, the opposite's true, but we're not going to go there because that is not in according to our original hypothesis. So I know that these calculations may seem somewhat daunting, but I promise you once you practice them, they'll go by pretty easily, and the conceptual stuff shouldn't be that much different than what you're used to, and the 4 steps of the hypothesis test are the same, and you'll keep seeing them over and over and over again.